If you recall, in the last video, we covered section 5.3, in which we deduced some basic properties of some of the trig functions from the definitions, and then we plotted their graphs based upon these properties and their definitions of the definitions of the trig functions. And yes, that was 5.3, and in this video, we're going to cover 5.4, and that's we're going to look at some of the other trig functions. We're going to look at some of their properties, and then from their properties, we're going to try to plot their graphs. We really only need a rough plot or rough sketch, but we'll look at the book to get a more precise plot and sketch or plot or sketch of these graphs. Let me share my screen. So I'm not sure actually. Wait, hold on. I'm not sure which screen it's sharing. Screen 2. Okay. For some reason, it flipped my screens around. I'm not sure why. Well, hopefully it's the right screen. So this is 5.4. This is just section. Name of the section is more trigonometric functions or trigonometric graphs. So in one of the, I guess, primary properties that we deduced about the sine and cosine was the fact that it's a periodic function, that it repeats. In some sense, it repeats. So let me just remind you of what that means. So we have a function from the real numbers to the real numbers. So the domain is the real numbers, the codomain is the real numbers. The image doesn't necessarily have to be equal to the domain, remember. And we say it's said to be periodic if there exists some number p, some real number, and this is called period of the function. So it's said to be periodic, and this is the period of the function, such that f of x plus p is equal to f of x for every x, for every real number x. Oh, I guess I did it again. Oops. So for every real number x. So we deduced that in the last video, we deduced that cosine and sine have a period of 2 pi. And what that meant for us is that one thing it meant for us is that when we want to plot the sine and the cosine function, all we need to do is look at its plot over an interval of length, 2 pi. So we graphed sine and cosine over the interval 0 to 2 pi. So these equations hold. These set equations hold for every real number x. Now we want to deduce. So, well, first, yeah, we want to deduce the period. Well, it's going to turn out the other trig functions are periodic, and that sort of makes sense because the other trig functions are defined in cosine, in terms of sine and cosine. Now, it's not always the case that if you start with a periodic function and then you define it, at least it doesn't always seem to be the case that if you take a periodic function and then you define another one in terms of it, it's not necessarily going to be periodic itself, but it turns out that the other trig functions are nice enough that they turn out to be periodic as well. So we have, if you remember, the cosecant is defined in terms of sine. It's 1 over sine x. So that immediately implies, it's pretty obvious that that immediately implies that cosecant x is also periodic with the same period. Sorry. So x, so it immediately implies that this equation holds. So cosecant is a periodic function with period 2 pi. And we have secant x is defined as 1 over cosine x. And again, that just immediately implies that the secant function is also periodic with a period of 2 pi. And these equations hold for all x. So these two equations hold for all x. But what about tangent? Well, it's not, if you remember, a tangent is tan x is defined as sine of x over cosine of x. So it might not be immediately obvious that this is the tan function is periodic. And in fact, we have to actually be careful because tangent is not defined wherever cosine x is 0. So because if you plug in, say, pi over 2 into tan x, cosine pi over 2 is 0, so this won't be defined. So not defined for cosine x equals 0. So those values of x for which cosine x is 0 is not defined. Well, that implies that x, if it can't be things, it can't be pi over 2, it can't be 3 pi over 2, or anything of the form pi over 2 plus pi n for any n that's an integer. So that what that means is that the domain of tan x is all of r except for the numbers of the form pi over 2 plus pi n for n, some integer, for any integer n. So you can't plug those into tangent. So we have to be a little more careful. But it turns out that the tangent function has a period of pi. And why does it have a period of pi? Well, we got to go back to the definition of the trig functions, in particular tangent, which is defined in terms of sine and cosine. And how were they defined? They were defined in terms of the unit circle. So we got to draw a unit circle. So I've been writing x, but I'm just going to look at tan of t. So if I give you a number t, so t, well, let's just, for simplicity, take t to be some positive number. So you start at your reference point 1, 0. T determines some point on the circle, say here. So you travel along this arc right here. This determines point x and y. So what that means is that sine of t is equal to y by definition, right? This is a definition. These are, by definition, sine of t is equal to y. And cosine of t is equal to x. And suppose I gave you a t value that's not of this form right here, right? So in other words, you can't be, this t doesn't land you here, or t doesn't land you here. You avoid those points. Otherwise, cosine of t would be 0, and the tangent wouldn't be defined. So we land on any one of the points on a circle except this point and this point. But for simplicity, we'll just say we land in the first quadrant here. Now, if I travel, so I travel t, but then if I travel pi, that's like 180 degrees, right? Well, pi is the same as 180 degrees. So it means I travel like diametrically. I go all the way around to maybe here. So these points are like diametric on the circle. So I land over here. Well, if they're diametric, it turns out that well, let me just point out. So this is, I get to this point by traveling t plus pi. I get to this point by traveling t. And it turns out if you travel t plus pi, you get to this diametric point on the circle. It's, you know, it's diametrically opposed to this point. This point right here, the one we get to by traveling a distance of t plus pi is diametrically opposed to this point, which we get to by traveling just t. It turns out that the coordinates of this are negative x and negative y. So what that means is tan of t plus pi is equal to, by definition, sine of t plus pi over cosine of t plus pi. So by definition, sine of t plus pi is equal to negative y, and sine of, or cosine of t plus pi is equal to negative xy. Remember this, the sine and the cosine just pluck out the y and the x coordinate respectively. Now they're both negatives because I mean, and when you're in the third quadrant, the x and y coordinates are negative. They're going to be negatives of whatever these coordinates are, and we're just saying that the coordinates of this point are x and y, so the coordinates of this will just be the negatives. But if they're both negative, those negatives cancel out. We'll just get y over x. But by definition, y is equal to sine of t. And by definition, x is equal to cosine of t. And then again, finally, by definition, sine of t over cosine of t is tangent of t. So what we've shown is that tan of t plus pi is equal to tan of t. So we use the definition. So to prove this identity, we use the definition of tan of t in terms of the unit circle. So this proves that tan of t plus pi is equal to tan of t. And without loss of generality, we chose t to land you in the first quadrant, but it would have just worked for any t. So this holds, this equation right here holds for all t, any real number t, except those points that we ruled out, pi over t plus n pi, which corresponded to these points. These are points where the circle is not defined. I mean, these are points where the tan function is not defined. Those are points on the circle. So that's that. Let me just stop sharing my screen for a second. Sorry about that. So it's going to turn out that these points, so we just determined that the period of tangent function is pi. And so what that means, if you recall, the cotangent function also has a period of pi, because cotangent is defined as 1 over tan of t. That's one way of defining the tangent function. So cotangent of t has a period of pi. It's a periodic function. So now we've determined that every trig function is periodic. And now there's some further properties that we can deduce for the tangent function and the cotangent, and actually all the other these reciprocal tan functions. So tan, cotan, secant, and cosecant. So because these functions are defined as reciprocals, they have these points in the domain where they're not defined, and it's going to turn out that these points, there will be like vertical lines going through these points, and there'll be vertical asymptotes for the reciprocal trig functions and tan itself, because tan is defined as sine over cosine. So those points where cosine is 0 will be where vertical asymptotes are for the tan function. So let's look at that for the tan function. So again, it's always good to write down the definition of the tan function or any of the functions, and they'll help us determine the properties that we're interested in. So we have sine of t over cosine of t. So again, this is defined everywhere except pi over 2 plus pi n for any integer n. So because this has a period of pi, we really only need to look at what it looks like on an interval of length pi. So it's not defined at, what this means is that it's not defined at negative pi over 2 and pi. Well, it turns out the open interval from negative pi over 2 to pi over 2 has length pi. So we only need to look at the behavior of the tan function over this interval right here. Notice it's not square brackets, it's parentheses, because tan is not defined at negative pi and pi. So, well, what's going on? We want to know what's happening near these points. Well, when t, let's just look at pi over 2 first. So when t is getting close to pi over 2, so how we express that notationally is that we're saying t is approaching pi over 2, and we're going to say from the left. So we use this like superscript notation. This negative to mean to the left of. When t is approaching pi over 2 from the left, because we only care about values of t to the left of pi over 2. We don't care about values of t to the right of pi over 2. When that's happening, sine of t is actually approaching 1, right? And actually sine of pi, because remember this is this notion of limits that I introduced a while back. Because it turns out that the trig functions are continuous on their domain. So when you take the limit, you can just plug in the limit value to your function. So the reason why sine of t over pi, or sine of t is approaching 1 as t approaches pi over 2 is because sine of pi over 2 just is 1. Remember, that's the point. If you draw your circle, sine of pi over 2 corresponds to this point right here. Well, the point that corresponds to the point 1, 0. So the y-coordinate is 1. So we can express this in even more concisely as the following. The limit of sine of t as t approaches pi over 2 to the left is equal to 1. Now, cosine is 0 at this number right here. So when you think about values getting really close to it, it's numbers that are very small. So cosine, so when you look at cosine of t, where t is a small number to the, or it's just left to pi over 2, cosine of t is going to be very small. It's going to be close to 0. And in fact, it's going to equal 0 when t is equal to pi over 2. So maybe I'll just write that in words. When t is very close to pi over 2 on the left, cosine of t is very small. I'm going to put these in parentheses because these are not really precise mathematically. I should say very small. You know, it doesn't really make sense to talk about a very small number, because if you take a number which you think is small, you can always have it and halve it. You take half of it, and it'll be even smaller. So there's no such thing as a very small number. But like we have this intuitive idea. But the idea is that cosine of t is getting very small. So when t is just some number just to the left of pi over 2, like very close to pi over 2, cosine t will be very close to 0. It'll be very small. So it'll be some like fraction maybe. So it'll be some number very close to 1, very close to 0. So that means that tan of t is equal to 1 over some very small number. Well, if it's, and this is all, like, put this all in quotations because this is not very rigorous at all. But if tan over t is equal to 1 over some small number, 1 over some small number is a large number. And in fact, as the denominator becomes smaller and smaller, which corresponds to t getting closer and closer to pi over 2, tan of t is just getting bigger and bigger and bigger. It's approaching infinity. So what that means, so this whole discussion can be summarized as follows. So that if we take the limit of tan of t as t approaches pi over 2 from the left, it's going to be infinity. It's going towards infinity. It's getting bigger and bigger. So what this implies is that x equals pi over 2 is a vertical asymptote. The line that the graph of tan t approaches but never touches. And you can do this whole same discussion. So the limit of tan of t, a very similar analysis applies to this following limit. When you take the limit of tan of t as t approaches negative pi over 2 from the right is equal to, but the only difference is it's going to be negative infinity. Remember, because when you take tan of a negative number, you can pull the negative out, and you're just plugging in tan of that, whatever that number is. Remember, tan of negative t is the same as tan of t. That was one of the properties we deduced in the last section. So what this implies is that x is equal to pi over 2, negative pi over 2 is a and in fact pi over 2 plus n pi is a vertical asymptote. This pattern is just going to repeat. Remember, this is a periodic function. It is a vertical asymptote for every integer n. So if you plot, so we got these two vertical lines, and the graph is approaching it somehow. And if you, I'm not going to go through this part, but if you take, you can make a table here. I'm going to pull the book up now. If you, you can make a table here and look at some values of tan of t. You can get an idea of what the graph looks like. You just plot some points. I won't go through that. But see, look at here. So pi over 2 is approximately 1.57, etc. And look at as t or x in this case is getting closer to 1.57, etc. Look at the numbers; they're getting bigger and bigger and bigger. So it's growing, or it's going towards infinity. And in fact, we can use all this to look at what the plot looks like. So get a picture of what the plot looks like. So here's one of the vertical asymptote, pi over 2, and here's negative pi over 2. And it's approaching that. It's getting very close to that line, but never touches it. Same thing right here, negative pi over 2. It's getting close to it, but never touches it. And you can do all this same analysis, and you can get that this is the graph of cotangent of x. It's kind of you just flip it in some sense. But notice the difference. It's the points where it's not defined is different. So cotangent is not defined wherever sine is 0, sine of t or sine of x is 0, because cotangent is reciprocal tangent. So cotangent is equal to cosine of x over sine of x. So sine of x is 0 at the points like 0, pi, 2 pi, 3 pi, 4 pi, etc. So cotangent of x is defined everywhere except that numbers of the form pi times n, where n is some integer. So that's where you're going to get vertical asymptotes at multiples of pi. So you get 0, pi, 3 pi, 4 pi, negative 2 pi, negative 3 pi, negative 4 pi. And here is a graph on a larger scale. See how it repeats? So this is tangent right here. It just repeats in this way, and it repeats in that way. So really, for tangent, you just need to know what the graph looks like from negative pi over 2 to pi over 2. For cotangent, you really only need to know what its graph looks like from 0 to pi. So let's do a similar analysis for cosecant, and then this same sort of analysis will apply to secant. Sorry. Computer's bugging out. So we have cosecant, and if you recall, that's defined to be 1 over sine of x. So what that means is that its domain is every real number, except wherever sine of x is 0. And that's, as I said, happens when you have a number of pi times n for any n which is an integer. So these are going to correspond to these points where it's not defined. They're going to correspond to vertical asymptotes. Why? Well, it's the same sort of a limit analysis we did up here. So when let's just think about pi, for example. When you take sine of pi, it's 0. Now, when you're on the left of pi, if you have a number really close to pi, sine of that number is going to be small. And so 1 over that number is going to be large. So cosine is getting, our cosecant is getting big as x or t approaches pi. So it's going to get larger and larger and larger. And of course, you can make a table and to find out some more values. So like you can make a table of values where cosecant is defined and get some numbers, and then you can get a better plot. I won't go through that because that's basically some of the homework. Of course, if you need help with that, you can always just email me and we can figure it out over email, or we can make a Zoom meeting. But if you take x as x approaches pi, it's going to be infinity. In fact, that's going to generalize. If you take x, the limit as x goes to any number of the form pi times n, one of these points where it's not defined, it's going to correspond to a vertical asymptote. And so the limit of cosecant of x as x approaches this is going to be, I got to be careful here because it could approach positive or negative infinity. So maybe what I'll do is I'll say the absolute value of this will be infinity. Depending on, I think so. Maybe actually I'm screwing myself up. Yeah, depending on what multiple of pi you approach, it's either going to approach positive or negative infinity. So let me pull up the graph and then we can look at some of those limits. So we have pi. So actually at every number it's going to be a different number. I'm sorry. So at every multiple of pi, depending on which side you approach, it's going to approach positive or negative infinity. So we have pi. If you approach, and this is the example we looked at, if you look at x as x approaches pi from the left, the graph is going to positive infinity. But if you take values of x to the right of pi, your cosecant, remember that's 1 over the y-coordinate, the y-coordinate is going to be negative. So it's going to approach a negative infinity. It's going to be a very large negative number. So it's going to negative infinity, and that pattern just repeats. And here's the graph of secant x, and you can do the same sort of limit analysis. And this is all just from the definition. It's just so this, sometimes it's, it seems like we're just pulling these graphs out of thin air. But these graphs can be found by just going to the definition, doing this limit analysis, and also plugging in values here. Like if you plug in pi over 2, you get 1. If you plug in pi over 2 to cosecant, you get 1. And if you plug in some other numbers, you can find out, based on the definitions of what those numbers are going to be, and you'll get a reasonably accurate graph, for our purposes at least. So all of this comes from the definition. Everything you see, it can be deduced from the definition. So always just, if you got those definitions in your head, you should be able to deduce these things and prove these properties on your own. Maybe not 100% rigorously, because we haven't looked at any of these things with terribly, it's not 100% rigorous, these proofs that I've given, but you can get a good idea of what's going on just looking at the definition. So everything is from the definition. So remember the definitions and you should be fine. So let's maybe look at some examples. So I'm not going to, these don't involve plotting, and as I said in my last video, this tablet isn't the best for drawing these graphs, so I'm just going to pull the book up again. So this is example 1. We have these two graphs. We have 2 times tan x, and then the other part is y is equal to negative tan x, and we want to graph these. So the first, let's look at b. That one's not bad. So this, remember, negative is just a reflection around the y-axis. So tan x is in blue, so that's that's what the graph looks like. That's what we deduced from here. And so you're just going to flip it about the y-axis, so it becomes the red curve. Now, when you for part A, when you multiply by 2, you're just you're stretching it. And notice this, in this case, 2 is not the amplitude of tan x. Because remember, amplitude is a max value. It's some real number that's like bounds the function. So we saw that sine and cosine have amplitude. They're bounded between 1 and -1. We drew those vertical or horizontal lines. Those horizontal lines bounded the functions. So they actually went through there. They intersected those two lines. So those were the max values. But the tan and the cotan and these other reciprocal functions, trig functions, they don't have amplitude because they don't have a max value. They're unbounded functions. They go off to infinity and negative infinity. So 2, you wouldn't say that 2 is the amplitude of the tan function in this case. But we can still plot 2 times tan x, and the 2 will be it'll stretch the function. It will that's what that factor in the front, that 2 does in the front. So it's sort of a vertical stretch. So notice at pi over 4, the graph is like the graph of tan x is like about here, but because you multiply to get this function 2 times tan x, you multiply by 2, so it's going to be higher up. So that's where that point is. So it's stretching it vertically. It's not a vertical shift. It's just like a vertical stretch. Okay, so now, although the tan and cotangent don't have amplitude, it doesn't make sense to talk about the amplitude of a function. We have seen that you can talk about a period. These functions are periodic, and that's the first thing we proved about the tan function. So if you take this, if you consider this function a times tan of x, the a is going to correspond to, depending on whether it's positive or negative, it's less than 1, or if it's greater than 1. It could do any number of things. And a could reflect it. If it's negative, it could stretch it vertically if it's some number greater than 1, or it could shrink it vertically if it's some number between 0 and 1. But the main focus is this value of k. So we have a times tan of kx, and we're going to just assume that k is positive. The negative case is easy, right? Remember, if k is negative, you can factor out that negative, and it all just reduces to the case of k being positive. So if our function f of x is equal to this, then as k of x varies from 0 to pi, that's the period, f of x completes one period, right? So it repeats, so it starts at 0 and then it ends at pi. It'll be the same value. Those two values will be the same. And then after that, it just keeps repeating. So when k of x is between 0 and pi, the function repeats itself after you've gone outside that interval. But we can solve for x to get this, pi over k. And so if the function repeats itself as kx goes from 0 to pi, solving for x, we see that the function actually repeats itself as x alone varies from 0 to pi over k. So that means that f of x, which is a times tan k of x, has a period of pi over k. So it repeats itself over intervals of length pi over k. So, and the same thing for cotangent. So to graph a times tan of kx, just graph it. Graph it over the inner. Sorry. Graph it over the interval negative pi over 2k to pi over 2k, because this length, the length of this interval will be pi. Or the length of this interval will be pi over k, and we know that the function repeats itself over intervals of pi over k, intervals of length pi over k, and then to graph a times cotangent of kx, you just graph it over the interval 0 to pi over k. Okay, so let's look at an example. So this is example 2 in the book. So we have the function 2x, tan of 2x, and tan of 2 times x minus pi over 4. So for this one, the k will be 2, so the period will be pi over 2. And then based upon this fact right here, which I wrote down, you just need to plot it over pi over k, pi over 2k, but k is 2, so it's pi over 4 to negative pi over 4 to pi over 4. And the graph is just, it almost looks the same as just tan x, but remember the two, when you multiply the input first, so remember that there's a difference between, let me try it. So it's not always the case. Oops. It's not always the case that f of 2x is the same as 2f of x. And the difference is that f of 2x corresponds to shifting or stretching it horizontally along the x-axis, because you're taking input x and then you multiply by 2, so you're stretching it along the x-axis, whether it's positive or negative, depending on whether x is positive or negative. But this 2 times f of x is, you're taking every output, so you plug in an x, you get an output value from the function, and then you stretch it. That will correspond to a vertical stretch. So you stretch it. If you were to overlay tan x and tan 2 of x, the tan 2 of x would be like a little wider, the graph. And then this one is not that hard to do. The period is going to be the same, and you just graph it over basically the same interval, I think. Yeah, you just shift it to the right. Remember, when you subtract off, that means you shift to the right. Okay, so that was example 2. And I won't go over example 3. It's basically the same. And let's see, so I'll just write this one last thing down and then we'll call it a day. So I won't go through the proof as I have been. I mean, not everything I've mentioned is really a proof. It's just like a heuristic or intuitive argument. But that's good enough for our purposes. So let me just write down a fact, and you can look in the book and it can tell you why this is the case. So we have, it's a similar result for cosecant and secant about the period of a function, these functions. So if you have f of x is equal to a cosecant of kx, and g of x is equal to a secant of kx, and I should say that, again, k is some positive number. The functions f of x and g of x have a period of 2 pi over k. And that implies that really you only need to look at their graphs over the intervals 2 pi over k. So they complete a whole period on this interval. And you can look at, so all the other graphs that you'll encounter will be some transformation, whether it's some like a shift vertically or horizontally, or stretch vertically or horizontally, or some sort of reflection. So as long as you know those basic graphs, you can deduce the other ones. So that's all for now, and then I think this should be enough for you to finish the homework.